In videos 1 to 9 of this series, we looked at the spin of electrons, tried to find out what we mean by spin, especially as it relates to angular momentum and magnetic moment, and also looked at some of the strange, non-classical behaviour of electron spin. This led us to delve into some of the mathematics of quantum mechanics, which in turn took us into thinking about how the postulated basis states of two electrons, up, 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 down, down, up, and down, down, could be combined in ways to help to explain the quantum entanglement of two such spins. In thinking about that entanglement, we got to the point where we believe that when two electrons with their individual magnetic moments come together, they can become entangled such that their spins are in anti-alignment. And by spin, you'll recall that at this stage we're thinking about spin magnetic moment, which we chose to draw as a red arrow associated with each electron. We also realized from the mathematics and from experiment that we can't really talk about the pair of entangled spins as pointing this way or that way, or any particular way, when they are entangled in this combined state. Rather, we had to bend our minds to think in terms of the spin of individual entangled electrons pointing in any and every direction in space, or even perhaps no direction, and at the same time somehow keep hold of the fact that the spin of one of the electrons was always in the opposite direction to that of the other. We illustrated this by drawing the electron with multiple red arrows for the magnetic moment. Even when the electrons in the entangled pair were separated, they remained in an entangled state, and it was impossible to think in terms of the individual spins of either of the electrons as having a definite direction in space. All we could say is that the spin of electron A is opposite to that of electron B. If you were to measure the components of the spin of one of the electrons in a particular direction, say electron A, there would be a 50-50 chance of the measurement coming out +1, namely in the direction you chose, or -1, opposite to the chosen direction. And the same would be true if you first measured electron B instead of A. However, once one of the electrons is measured, let's say A, and let's say its spin turns out to be up in the Z direction, then immediately the spin of B could be said to have a definite spin direction, and that would be down in the Z direction. So, if at that point you then measured the components of the spin of electron B in the Z direction, you would definitely get the answer to be down. There would be no question of a 50-50 chance as before. It would definitely be measured as spin down because electron A had already been measured to be spin up. Of course, if after having measured the spin of A to be up in the Z direction, you then measured the component of the spin of B in any other direction, then the usual rules of quantum mechanics for a spin pointing down would apply. For example, measure it in the X direction, in other words at 90 degrees to the Z direction, and there would be a 50-50 chance of it being in the plus or minus X direction. Another example would be that if, after having measured the spin of A to be up in the Z direction, you then measure the component of the spin of B at, say, 45 degrees to the Z axis, like this, there would then be about a 15% chance of measuring the spin to be in the direction shown here by the measuring device, and about an 85% chance of finding the spin to be in the opposite direction. You may recall these numbers 85% and 15% from when we discussed some of the details of quantum mechanics. These percentages essentially come from cos squared theta over 2 and sine squared theta over 2, which for 45 degrees give the two probabilities as 0.854 and 0.146, which I usually rounded off as 0.85 and 0.15, which gave us our 85% and 15% probabilities. That's what I mean by what we have come to take as the usual rules of quantum mechanics. After entanglement, once the spin direction of one of the electrons is measured, the other one is, in a very limited sense, fixed. In other words, you can say with 100% certainty what you would get if you measured it in one particular direction. But if you measure it in any other direction, the usual rules of quantum mechanics mean that you could get any possible answer, and the probability of which answer will depend on the angle you choose. However, Going back a few steps in this discussion, that idea that once A has been measured, there is an instantaneous and definite alignment of B in the opposite direction should strike you as rather strange, just as it did to those people first investigating the physics of the very small. To put it in naive terms, how does the second electron know that it must change from being totally uncertain about its spin direction, with a 50-50 chance either way, to being very definitely in a particular direction, namely the opposite direction to the one in which the first electron had been measured to be? Do they communicate with one another? Does the first electron somehow tell the second electron what to do just at the right time? How is it done? And this was the great debate within quantum mechanics in the 1930s. Is there a satisfactory explanation? Well, although most people might suggest all sorts of ideas to explain this strangeness, the conclusion that most people come to is that one of two things must be going on. And here are what seem to be the two best contenders for an explanation. One possibility is that when the electrons come together and become entangled, certain variables or data inside the electrons that we as outsiders have no access to and therefore cannot know, take on correlated values for each of the electrons. In other words, within each A electron, there would be information carried along with it as the two electrons separate. And that information would effectively tell it which way for the spin to point if measured in any direction in space. Of course, the information that B would have embedded in it would have to be exactly the opposite to the information contained in A. For example, one piece of information might be that A would know that if the component of its spin were to be measured in the Z direction, it has to point up +1. B, of course, would have the opposite information, so that it would know that if the component of its spin is measured in the Z direction, it must point down -1. But that's just for one pair of entangled electrons. Other pairs of entangled electrons might have different information for the Z direction. Say that the A electron must point down if measured in the Z direction, and the B electron must point up. The 50-50 nature of the first measurement would still be true, providing nature produced just as many pairs of electrons where A was told to be up as where A was told to be down. But also that's just for getting the Z direction right. Each electron in each entangled pair would have to contain information about the X and Y directions as well, and in fact every direction in between. Now that's a lot of information for each electron to hold for every direction in space, even if they store that information in some kind of algorithm. But it would certainly mean that in a classical way we could make sense of what happens in practice. It would be frustrating that we can't know what these variables are or how they are held within the electrons, but at least it would allow us to get our head around how the second electron can know what to do at the instant that the first electron is measured. That's one possible solution to the conundrum, what has been called hidden variables. A second possible solution in some ways centers on the idea of making more of the fact that these entangled electrons are in a kind of combined state, the singlet state. We should perhaps think in terms of, and this may not be the best kind of language for me to use, but I'm going to say it anyway, we should think in terms of there being some kind of instantaneous communication between the two electrons, or rather instantaneous communication within the singlet state. We've already suggested in an earlier video that who measures the spin component first is not necessarily a problem for this kind of instantaneous communication solution, which really relates to instantaneous state vector collapse. And this will be discussed in a little bit more detail later. But for now, I want simply to suggest that we have these two possible ways of explaining the spin decisions, or at least thinking about them. Number one, there are hidden variables. Each electron knows what to do for every scenario. They each have the information they need even before measurements are made on either of them. And number two, the whole of the singlet state collapses instantaneously, giving a form of instant communication from one electron to the other, or rather within the singlet state. Now these are two very different solutions to making sense of the problem. The one, hidden variables, which was favoured by Albert Einstein in the early discussions around quantum mechanics, is in a sense more classical in nature. It fits in with a kind of local reality whereby things are only really affected by their immediate surroundings. It's easy to understand the idea in principle, but of course frustrating having to postulate a multitude of variables that we can't know anything about. The other solution, the instantaneous collapse of the state vector or wave function, was favoured by Niels Bohr, one of the fathers of quantum mechanics. This idea appears to allow for instantaneous communication between the two electrons, and is perhaps more difficult for most people to accept. It certainly was for Einstein. It seemed to fly in the face of the idea of local realism, in that the second electron gets its direction of spin affected by a measurement made on the first electron, and the separation of them could be extremely large, possibly light years. Now that's certainly not local reality. It seemed in that early stage of quantum mechanics in the 1930s that physicists were stuck with two explanations, neither of which seemed ideal, and there was no way of deciding between them. It was in 1964, however, that John Bell came up with an idea to test between the two. He derived a simple mathematical formulation based on simple classical logic which could perhaps eliminate one of these explanations. He came up with what you could call an inequality, and if it is applied to an entangled pair of electrons, for example, ought to be able to confirm or deny the possibility of the existence of hidden variables. The mathematical formulation is known as Bell's inequality or Bell's formula. And the argument is that the hidden variable explanation, being classical in nature and tied to local realism, ought to fit in with Bell's mathematical formulation, which itself was based on classical ideas. The question then would be, does the practical outworking of the real world, the actual measurements of things, fit in with Bell's inequality? If they did, then the hidden variable idea was a possible explanation of what was going on. If they didn't, then the hidden variable idea would have to be abandoned, and the only real alternative would then be the instantaneous state collapse idea. So that's where we're going from here. We'll first derive Bell's inequality, a totally classical idea. Then we'll look to see how, or whether or not, the theory of the hidden variables idea for a pair of entangled electrons agrees with Bell's inequality. I'll give you that result now and say that it will agree. The reason being, both ideas are classical in nature. Bell's inequality has a classical basis, and the hidden variable idea has a classical basis, but we'll show it anyway. We'll go through the mathematics of that. Then we'll see whether or not the predictions of the theory of quantum mechanics for a pair of entangled electrons agrees with Bell's inequality. Again, I'll give you the result now and say that there will not be an agreement. We'll find that one idea does follow Bell's inequality and the other idea doesn't. And that sets us up for a test of the two ideas by asking the question, what about experimental reality? So finally, we'll look at the actual results and predictions of experiments. If Bell's inequality is not satisfied when applied to the actual results for a pair of entangled electrons, then it would mean that the hidden variable theory would have to be abandoned. Bell's inequality will have helped to dispense with the hidden variable idea. So, to start with, what is this classical mathematical formulation known as Bell's inequality? We'll discuss what it is, how it's often written down, and how it's used, and then we'll see how it can be applied to quantum entanglement in order to try and distinguish between these two ideas. Well, as most physics teachers do nowadays, it seems best to me to think through Bell's inequality using simple set theory. I'm going to do it this way. Think of three properties that an object can have. By object, I will eventually mean an electron, and by property, I will eventually mean the component of the spin direction, but for now, in order to get our head around this classical idea, we'll think of any kind of object and any kind of property it can have, provided we can couch that property in terms of a dichotomy: yes, no, is it, isn't it. You'll see what I mean if I take as my example for this discussion a pair of socks, or maybe just one sock of a pair, and I'll take my three properties of the sock as three possible coloured hoops on the sock that the socks have or don't have. Let's suppose that a sock can have a red or a blue or a green hoop in different positions down the sock. Or they can have any pair of these coloured hoops, a red and a blue, a red and a green, or a blue and a green. Or they can have all three colours, or no coloured hoop at all. I'm sure you can see from this that there are obviously 8 possibilities, 2 to the 3, and we could put these 8 possibilities into a table like this. The pluses and the minuses here indicate whether a sock has or doesn't have a particular coloured hoop. For example, this row represents a sock with no coloured hoops. The minus sign means no colour, no red, no blue, no green. This row represents a sock with a single red hoop. The plus sign means it has that colour. This row is for a single blue, and this for a single green. This row represents a sock with both red and blue. This is for red and green, and this is for blue and green. And finally, the bottom row represents a sock with all 3 coloured hoops on it: red, blue and green. Now suppose we had a large number of such socks with random numbers of each of the 8 types. We could rewrite the table and put in an extra column for the numbers of each different type of sock. I'll call these 8 numbers N0 to N7. N0 will be the number of socks with no hoops on them, and N7 will be the number with all 3 coloured hoops on them. The total number of socks, of course, could be written as NT, N total, where NT is given by the sum of N0 to N7. Okay, I hope there's nothing difficult so far. We're just imagining lots of coloured socks. The numbers N0 to N7 are just random numbers of each. From something like this, John Bell essentially said that according to classical theory, or rather common sense, the number of socks with a red hoop but not a blue hoop, plus the number with a blue hoop but not a green hoop, must be greater or equal to the number of socks with a red but not a green hoop. And that's it. That's one version of Bell's inequality. If that's not already obvious to you, there are a number of ways of seeing that this inequality must be true for this situation with coloured socks. N0 doesn't come into it. The formula doesn't mention socks with no coloured hoops. So let's put the numbers N1 to N7 into Bell's inequality where they should be. The first term in Bell's inequality has to be the number of socks which have a red hoop but not a blue hoop. Doesn't matter about green. And clearly from the table, if you look at it, there are only 2 rows that have a plus in the red column and a minus in the blue column. So the number with red but not blue hoops is obviously N1 plus N5. Similarly, the second term in Bell's inequality is the number of socks which have a blue hoop but not a green hoop. Again, it doesn't matter this time about red. From the table, only these rows have this makeup of colours, plus in the blue and minus in the green. So the number with blue and not green hoops is obviously N2 plus N4. Finally, the term on the other side of the inequality is the number of socks which have a red hoop but not a green hoop. Again, it doesn't matter this time about blue. Looking at the table again, the number with red and not green hoops must obviously be N1 plus N4. If I now rearrange these numbers on the left hand side and put them in a different order, then the inequality is saying that N1 plus N4 plus N2 plus N5 is greater or equal to N1 plus N4. Now, if we assume that all the N numbers are either positive numbers or 0, we can't have a negative number of socks, then the fact that the left-hand side contains n2 plus n5 more than the right-hand side means that the inequality must be true for this sock situation. Bell's inequality, this formula, in a way, states the obvious for a classical situation. The proof shown here with socks simply is stating the obvious. As an aside, some people prefer to prove the inequality using Venn diagrams, where you would show the overlapping variables as overlapping circles. These are the three colours in my case. N0 may well have a large number of socks, but they would be out here and not really involved in the proof. Any sock with a red hoop would be somewhere in the red circle, and similarly for blue and green. Red only is N1. Blue only, N2, and green only, N3. Red and blue and not green is N4. Red and green and not blue is N5. Blue and green and not red is N6. And of course the number of socks with all three coloured hoops is N7. As I said before, whichever way you choose to prove it, Bell's inequality is, in a way, fairly obvious for a classical situation. The question for us is whether we can somehow apply it to one of a pair of entangled electrons and see whether the inequality holds. It may then help us to distinguish between the appropriateness of the two possible explanations of entanglement, namely hidden variables or collapse of or communication within the singlet state. Before we start applying the inequality and testing it out, it's probably worth saying again that it should seem reasonable that Bell's inequality should be obeyed when it is applied to the hidden variable situation. The reason is that the hidden variables explanation is very much a classical idea, but we'll check it out anyway. The real crunch will come when we try to apply Bell's inequality to the quantum mechanical predictions for an electron which is one of an entangled pair, and then later to the actual results of experiment. In order to consolidate our thinking, let's just check out the obvious, whether Bell's inequality is obeyed for the idea of hidden variables being embedded in a pair of entangled electrons. As I've been saying, it should be, but it'll be good to show it. The hidden variable theory is a very classical idea, and so Bell's inequality, which is based on classical logic, should apply. We're testing the view here that when two electrons become entangled, they agree on the values of a number of internal hidden variables which relate to the direction that measurements of the components of the spin will have to give in particular directions. In a sense, the electrons will know beforehand what answers to give when asked questions about the component of the spin in a particular direction. Obviously, in doing this, we can't look at every direction in space for this test, so just as we limited our proof of Bell's theorem to three colours of the hoops on the socks, we will limit ourselves to three directions in space, and we look at the kind of hidden variables that will be needed for the two electrons to have opposite spins for each of those three directions. I'm sure you realise that a complete hidden variable theory would be much more involved than this, but it will be sufficient for this discussion. I will choose the following three directions in space, and I'm going to call them D1, D2 and D3. These are instead of red, blue and green. D1 will be the Z direction. D2 will be at 45 degrees to the Z direction in the XZ plane, and D3 will be in the X direction. Note that these three directions here are all in the plane of the screen. D2 is not into the screen. We're ignoring the Y direction. With our hoop colours for socks, the dichotomous issues were: is it red or not? Is it blue or not? Is it green or not? Here, with the three directions, our dichotomous questions will be: is it in the plus D1 direction or minus? Is it in the plus D2 direction or minus? Is it in the plus D3 direction or minus? Now you may think at this stage that the analogy with the sock colours is poor. After all, the socks could indeed have more than one colour at the same time. But an electron cannot have more than one spin direction at the same time, at least in the classical sense. However, I hope you will see in a minute that the analogy is a good one, because we will be talking about information in the hidden variables as to whether the spin is in a particular direction or not, if it's measured in that direction. In other words, we will be talking about the electron having information about more than one direction at the same time, which it obviously can and must. It must have that in this hidden variable model. The three dichotomous questions are really, if measured in the d1 direction, would it measure plus or minus? If measured in the d2 direction, would it measure plus or minus? And if measured in the d3 direction, would it measure plus or minus? Anyway, this should become clear as we work through things. In order to clarify this, let me take a first simple preparatory illustration of the hidden variable situation that we can now analyze for these three directions in space. Suppose the two electrons A and B become entangled, and the hidden variables that they agree on is that electron A will always give a positive result if measured in any of the d1, d2 and d3 directions, and electron B, because it's entangled, will always therefore give a negative result for those three directions. In other words, electron A will always give a measurement of +1 in any of those three directions, and electron B will always give a measurement of -1 in any of those three directions. I would picture that something like this. The three plus signs which I've put in the A electron are the hidden variables for A and relate to the three directions d1, d2 and d3. The electron would have to carry that information with it. If in this case the component of the spin of electron A is measured in any of these three directions, then the hidden variables within the electron A will tell it to give a positive result. The first cross is for it to always give a +1 if measured in the Z direction, that's D1. The second cross is to tell it to give a +1 if measured in the 45-degree direction, D2. And the third cross is for it to give +1 in the X direction, D3. I hope you can see that the electron can, in fact must, have information about more than one direction, just like the socks had information about more than one colour. It should also be obvious that the three minus signs in the B electron tell that particular electron that if the component of its spin is measured in any of the three directions, it must give a negative result. The component of the spin will come out as being in the negative direction along either D1, D2 or D3, depending which one is measured. We're obviously assuming that a plus in A must have an equivalent minus in B and vice versa, because we know that B must always be the opposite of A for a pair of entangled electrons in the singlet state. Okay, that's one example of what the hidden variables might look like. Here's another possibility. Another pair of hidden variables that the entangled pair of electrons could be carrying as they separate from each other. Minus plus minus for A and plus minus plus for B. Notice once again that what B carries has to be the opposite of what A carries. If electron A is told to give the measurement as negative in the D1 direction, then electron B must obviously carry the hidden information to give its measurement as positive in the D1 direction, and so on. Now clearly there are other mixtures of plus and minus that the electrons might need to have, even for just these three directions D1, D2 and D3. In fact, we could write a table out which would include all the possible sets of information that the electrons might have to carry with them for these three angles. And for the A electron it would look like this. The B electron, of course, would have to carry the opposite information. So in this simple model of only looking at three directions in space, any pair of electrons that became entangled would take on one line of hidden variables from the table. The A electron taking from the A table and the B electron taking from the same line of the B table. It might be this one from line 4, minus minus plus for A and plus plus minus for B. Or it might be any one of the 8 combinations in the tables. However, just as we assumed having a large number of socks of different colours, let's assume that lots of pairs of entangled electrons are created, and each pair takes from a line of the tables. Each pair may take from a different line. Once again, we would suggest that with so many entangled pairs being created, we could add a column to the tables for the numbers of electron pairs which take values from each line, and we could also label these, as before, N0 to N7, and we could put in the total number NT. Here is that table for electron A, and there would obviously be an opposite table for electron B with exactly the same numbers, N0 to N7. The entangled electrons are in pairs after all. I hope by this point you've got at least the gist of what's going on. We are making a total of NT entangled pairs of electrons, and in working through a hidden variable model we are assuming that N0 of those pairs have A electrons which have taken these hidden variables with them. N1 pairs take these, and so on. Of course, the B electrons in each pair will take the corresponding row of their table, and they'll always be the opposite. But from now on in this discussion, we'll only concentrate on the A electrons. The question is Bell's inequality satisfied for this simple three-direction hidden variable theory? I'm sure it's obvious that the answer must be yes. Not only is it a classical situation, but it is also so similar to the sock example that it must satisfy the inequality. However, for completeness, here's the working out. Bell's inequality for this situation, focusing on just the electron A, says that the number of A electrons that get information for the positive D1 direction but not the positive D2 direction, in other words the negative D2 direction, plus the number of A electrons that get information for the positive D2 direction but the negative D3 direction, must be greater or equal to the number of A electrons that get information for the positive D1 direction and the negative D3 direction. Now if you think about it, this is exactly equivalent to the sock situation. Again, N0 doesn't come into it. There will be electron pairs from the N0 line of the tables, but they're not involved in Bell's inequality. For the others, however, the number with plus D1 and not plus D2, that's minus D2, is obviously N1 plus N5. The number with plus D2 and not plus D3 must be N2 plus N4, and the number with plus D1 and not plus D3 is obviously N1 plus N4. Once again, rearranging the n's on the left hand side to make it more obvious, this means that Bell's inequality suggests that N1 plus N4 plus N2 plus N5 must be greater or equal to N1 plus N4. And again, assuming that all the N numbers are either positive or zero, which they must be, then this greater than or equal to in Bell's formula must be true. In other words, the inequality holds for what we might call this local hidden variable theory. That was the easy bit. That result wasn't really in doubt. The crunch will be when we come to look at Bell's inequality as it applies to the predictions of quantum mechanics, and then experimental results, which we believe are themselves in agreement with quantum mechanics. Will Bell's inequality go along with them? John Bell had said in effect that no local hidden variable theory can ever replicate the outcomes of quantum mechanics. So we might expect that when we look at Bell's inequality and the mathematics of quantum mechanics, the inequality will not hold. This would imply that anything like a local hidden variables theory which obeys Bell's inequality will not be able to reproduce the probability distribution expected from quantum mechanics. But we shall see. Before we get to that, however, I'd better move on to thinking more about probability distributions. The short discussion of Bell's inequality that we've had so far has involved assuming large numbers of entangled pairs, and then looking at the numbers of electrons in various categories within the Bell formula, N0, N1, N2, and so on. It should be obvious, I hope, that all of this discussion could have been couched in terms of probability, and we're going to need to take the probability approach if we are to move into thinking more about how Bell's inequality behaves in real life in terms of the predictions of quantum mechanics. If it's not already obvious to you that I can simply shift to working with probabilities, then just consider what we had for the hidden variable situation. Here is that hidden variable table again for electron A. It involved a large number of electron pairs being produced, which we called NT, for N total. Of these, N0 had a certain set of hidden variables, N1 another set, and so on. Bell's inequality was then written as the number of A electrons with information for a positive D1 but not a positive D2, plus the number of A electrons with information for a positive D2 but not a positive D3 must be greater than or equal to the number of A electrons with information for a positive D1 but not a positive D3. If, however, we divide this whole equation by the total number of electron pairs created, NT, we essentially have Bell's inequality in probability form. This, the number with a certain property divided by the total number, is the probability P that electron A will get information for the positive D1 direction but not the positive D2 direction. This is the probability P that electron A will get information for the positive D2 direction but not the positive D3 direction. And this, of course, is the probability P that electron A will get information for the positive D1 direction but not the positive D3 direction. This means that Bell's inequality can be written in probability form like this, where capital P stands for the probability. This says the probability that an A electron will get information for a positive D1 but not a positive D2, plus the probability that an A electron will get information for a positive D2 but not a positive D3, must be greater than or equal to the probability that an A electron will get information for a positive D1 but not a positive D3. In fact, the table for the A electron could reflect the probability idea if the 8 numbers, N0 to N7, were also divided by NT. Then N0 when divided by NT could be written as P0, the probability of electron A having the hidden variables minus, 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 and so on. We could then have for our A table this. And the probability version of the Bell's inequality for the hidden variable situation that we did a moment ago would come down to P1 plus P5 plus P2 plus P4 must be greater than or equal to P1 plus P4. This, again, is obviously satisfied for the hidden variable situation because the left-hand side has a P2 plus P5 more than the right-hand side. This is easily seen when the left-hand side is rearranged. These are the same, so the left-hand side is this much bigger. As I say, using probabilities rather than numbers and this form of the Bell's inequality will be important when thinking about its application to the known results of quantum mechanics. So let's get into what that will entail. The consistency of the hidden variable idea with the Bell inequality simply means that we have a way of framing a kind of locality and realism, or what we might call local realism, meaning that the existence of things don't depend on observation and on things that can instantaneously change them from large distances away. The hidden variables would do everything for us in getting the spins of the electrons correct. That's all fairly coherent, but does it agree with reality? That's the main question now. Is the Bell inequality consistent or not with the predictions of quantum mechanics, which as far as we know at this stage is consistent with experiment? If Bell's inequality is consistent with quantum mechanics, then in a way it's no different to the hidden variable theory, and so experiment would agree with both. The hidden variable theory in that case could be said to be a possible explanation of reality. If, on the other hand, Bell's inequality is not consistent with quantum mechanics, and experiment goes along with quantum mechanics as far as Bell's inequality is concerned, then the hidden variable theory would have to be discarded. To test this, we need to try and apply Bell's inequality to the rules of quantum mechanics. How can this be done? Well, we'll start with Bell's inequality in a probability form. And we'll stick with the definitions of three chosen directions in space that we will consider: d1, d2 and d3. You should recall that d1 is the z direction, d2 is the direction 45 degrees to the z-axis in the xz plane, and d3 is the x direction. In considering this version of Bell's inequality, we don't need to be thinking about lots of electrons and the numbers of this and the numbers of that and the other. The idea of probability encompasses all that. We can deal with just one electron of an entangled pair, let's say the A electron, and consider the probability of its spin being measured in various directions. If Bell's inequality then holds for the behavior of such an entangled electron under the rules of quantum mechanics, then we will find that the probability that electron A will give a measurement in the positive d1 direction and not the positive d2 direction if measured in those directions, plus the probability that electron A will give a measurement in the positive d2 direction and not the positive d3 direction if measured in those directions, will, if it holds, be greater than or equal to the probability that electron A will give a measurement in the positive d1 direction and not the positive d3 direction if measured in those directions. Now, I'm sure there are some people who are somewhat confused by these three statements. Look at the first of these. The probability that electron A will give a measurement in the positive d1 direction and not the positive d2 direction. What does that mean? Okay, it was easy to get our head around the equivalent statement for hidden variables. It was to do with the number of A electrons that carry information to be measured in the positive d1 direction but not the positive d2 direction, which in that case essentially meant the negative d2 direction. But this, the probability that electron A will give a measurement in the positive d1 direction and not the positive d2 direction. This seems to be more obscure. Well, I hope that in a moment it will become clear. That second bit of the statement, not in the positive d2 direction, will be reinterpreted later to focus on the B electron, and hopefully it will then seem reasonable. Anyway, we've got our Bell inequality in probability form for electron A. And we just need to work out these probabilities from what we know about the rules of quantum mechanics and see if the left-hand side is indeed greater or equal to the right-hand side. If it is, then Bell's inequality could be said to hold for quantum mechanics. If, on the other hand, the inequality does not hold for the predictions of quantum mechanics, then we have a clear distinction between what hidden variable theory predicts and what quantum mechanics predicts. We should then be able to test one against the other experimentally. So how on earth are we going to work out these three probabilities for an entangled electron A? Well, we could work through the mathematics of the quantum mechanics, which would probably take about an hour or so, and might involve introducing some other ideas such as projection operators and the like. Or we could cheat. Well, I don't mean cheat really, I just mean we could use some of the quantum mechanics we've already done and some of the results that we've already found to get a value for each of these three probabilities. This may not seem quite as rigorous as doing the other method, but it will give the correct answer and it will be easier, and the process of doing this way will give connections to reality much more than would churning through an hour or more of the mathematics. So here goes. Let me first rewrite this probability form of Bell's inequality in a more visual way by using small arrows to denote the possible directions of the spin of this electron A. You should at this point check in your own mind that the arrows that I have written do actually mean the same as the direction variables d1, d2 and d3. Crudely, d1 is the z direction, d2 is at 45 degrees to the z direction, and d3 is the x direction. Now, if you remember, at one stage I used colours to signify electron A and electron B. It was amber for the A, which look more like a red sometimes, and blue for the B electron. So let me colour the arrows amber to signify that we're looking for probabilities for the A electron. So in fairly loose language, we're checking for electron A that the probability for up and not 45 degrees plus the probability for 45 degrees and not 90 degrees is greater than or equal to the probability for up and not 90 degrees. That still might seem rather vague, but it will become clear in a minute, I promise. Now, to say not something is essentially to say the opposite is true. So not up must be the same as down, and not right must be left, and so on. We know that that's certainly true for electrons and their spin direction. Only two values are allowed. This means that we can replace these words not with the word and, providing we reverse the direction of the arrow which comes after them. In other words, Bell's inequality in probability form for entangled electron A can be written as the probability for up and down at 45 degrees plus the probability for 45 degrees and left at 90 degrees is greater than or equal to the probability for up and left at 90 degrees. Now this might all seem even more vague. How can it be up and also down at 45 degrees? But bear with me, because now comes an even bigger change, and it's the key to getting a result out of this inequality as we switch to electron B. The inequality is looking only at the probabilities for one of the two entangled electrons, electron A. That's why the arrows are all coloured amber. However, an important fact about an entangled pair of electrons like this, according to the rules of quantum mechanics, is that the directions of the spins of electron A and electron B are always found to be in the opposite direction to one another, even if we don't know that direction, and even if they don't yet have a definite direction, if that doesn't sound too stupid. So any requirement on the spin of electron A could be shown as the opposite requirement for the spin of electron B. I could change the direction of any or all of the arrows in this inequality by 180 degrees, providing I colour them blue as an indication that they refer to electron B. Let me first change this one, because an A electron down at 45 degrees means that we must have a B electron up at 45 degrees. So there's the blue arrow up at 45 degrees instead. Similarly for this one, an A electron with spin in the negative x direction means that the B electron must be in the positive x direction. And I'll change this one, which is the same as I've just done really. So this is the Bell's inequality that I want us to think about, and it now should make more sense. It has exactly the same meaning as before, but it's written now in a way that is easier to get your head around. You're not having to say in each term that the spin is one thing and something else. You're saying that the spin A is one thing and the spin B is something else. That means it's much easier to work out the probabilities. This inequality essentially says that for an entangled pair of electrons A and B, the probability of finding A up in the Z direction and B at 45 degrees in the Z direction, plus the probability of finding A at 45 degrees to the Z direction and B in the positive X direction, must be greater than or equal to the probability of finding A up in the Z direction and B in the positive X direction. Now we can do this. We've looked at enough situations where probabilities are 50-50, and we've also looked at 45-degree orientations where the probabilities are 85-15. So we should be able to think this through. Let's look at the first term. We want to know the probability that A is up and B is at 45 degrees. Let's imagine doing some measurements on this entangled pair of electrons A and B using the rules of the mathematics of quantum mechanics. We first come to entangled electron A, knowing nothing about it, and we measure the component of the spin in the Z direction. What is the probability that we will find the spin to be up in the positive Z direction? Well, the answer, of course, is a half. We found that if you measure the spin component of an entangled electron in any direction, then the probability of getting plus or minus in that direction is 50-50. The mathematics of that, if you recall, was such that we could write the state vector for the entangled pair before measurement in lots of ways, but one of them was like this, a combination of two of our basis states, up down minus down up, with the 1 over root 2 multiplying each of them. This could also be shown as this, and the 1 over root 2 squared tells us that there is a 50-50 chance of getting A up and B down, or A down and B up. So we know that if we measure the z components of the spin of electron A, there is a 50% chance of finding that it is up. Looking at the Bell inequality, therefore, we can say that the probability of finding the spin of the A electron to be up is 0.5. We also said that once we have measured the spin components of the electron A to be up, then the electron B must be down. In other words, the singlet state, which was this, collapses to the straightforward up-down state. So electron B now has its spin pointing down in the z direction. However, for our Bell formula, we now want to measure the components of that B spin in a direction of 45 degrees to the z-axis, whereas it's actually pointing down. This will again be a probability thing, and you should recall that the probability will go as cos squared theta over 2 and sine squared theta over 2, which for 45 degrees means a 1585 chance of being in the direction of 45 degrees or opposite to it. In the case of electron B actually pointing down, the probability of measuring the component of that spin upwards at 45 degrees is sine squared 45 over 2, which is approximately 0.15. Please remember that this is the probability after the spin of A has been determined. To have these two conditions met, A up and B at 45, means that we have to multiply the probabilities. So for this whole term, we get approximately 0.075 for the total probability of finding electron A with its spin in the positive z direction, and then finding electron B with its spin up at 45. So that's one of the three terms in Bell's inequality done as far as quantum mechanics is concerned. At this point, it's worth noting that it wouldn't have made any difference to the probability if we had measured the spin components of B first and A second. We'd still get 0.075. Think about it. You start by measuring the entangled electron B at 45 degrees to the z-axis. There's a 0.5 chance of it pointing in this direction. That's our 0.5. The spins of the electrons are now both at 45 degrees but in opposite directions. Coming then to the A electron, the second electron, it must now point in the opposite direction to B, down at 45. So what's the chance of measuring it to be up in the positive z direction? Well, again, there is 45 degrees between them, so it's a 1585 split, and the chance turns out to be 0.15, which when multiplied by the 0.5 would give the same overall figure as 0.075. This idea that the ordering of measurements didn't matter to the outcome was mentioned earlier when we were discussing who measures which spin first. Also, before we move on, you should realize that we have used the mathematics of quantum mechanics here to give us things like sine squared 45 over 2 and the value of 0.15, as well as the value of 0.5 for the 50-50 measurement. This is not based on any experimental measurements at this point. We're working through the idea of quantum mechanics applied to Bell's inequality. Okay, that's the first term in our Bell's inequality for quantum mechanics. So what about the second term? Well, if you think about it, it's going to give us exactly the same result as for the first term, 0.075. The two requirements, one for A and one for B, are once again at 45 degrees to one another. You measure one of them, there's your half. The other spin must then be in the opposite direction, but you measure it at 45 degrees, so there's a 1585 split. Because of the directions, you have to take the 0.15 as the probability. Put the two together, you get the probability for the whole term, and it is obviously 0.075. So the only question now is whether the sum of the two terms on this left-hand side are going to be greater than or equal to what we find on the right-hand side. We need now to calculate this probability, and this is also very easy. We want to know the probability of A being measured to be up and B being measured to be at 90 degrees. We start once again with the electrons entangled, so they don't have a spin direction. We'll imagine measuring the spin component of the A electron first, although it doesn't really matter about the order. We measure the Z component of the spin of the A electron, and the probability of getting the answer that the spin is up will once again be 0.5. Once that is ascertained, then the spin of electron B must point downwards in the Z direction. But we want then to measure the component of the spin in the X direction, in other words, at right angles to what it is. Now, from all that we have done, it should be obvious that this is a 50-50 split. So the probability of getting the result that the spin component of B is in the positive X direction will be 0.5. Once again, we have to multiply these two things together because we want the probability of finding electron A with its spin in the positive Z direction and electron B with its spin in the positive X direction. This multiplication gives 0.25. Adding the terms on the left, we end up with an inequality which says 0.15 must be greater than or equal to 0.25. We have, according to quantum mechanics, an inequality that does not hold. 0.15 is not greater than or equal to 0.25. In other words, from the behavior of entangled electrons according to quantum mechanics, it is clear that the Bell inequality is not satisfied. The argument suggested earlier was that the hidden variable theory, which is tied to local realism and classical thinking, ought to satisfy Bell's inequality, and of course it did. Then we moved on to looking at quantum mechanics just now, and we found that that doesn't satisfy Bell's inequality. The next part of our concern is, in a sense, what about reality? Does it follow the results predicted by hidden variables, or the results of quantum mechanics? Well, even though in the next couple of videos we will look at actual experiments to test this, it should be fairly obvious from results that I've been touching upon during this series of videos that quantum mechanics gives the best prediction of reality. And the fact that Bell's inequality is not satisfied by quantum mechanics means that we can't support the very classical idea of hidden variables as a way of explaining the idiosyncrasies of entanglement. The only real possibility within what we've looked at is quantum mechanics. And that means we're left with this rather strange idea of the state vector collapsing instantaneously, which in itself has all the hallmarks of some sort of communication, perhaps, within the singlet state. This seems the only way to explain how one electron can know what to do once the other electron has had the component of its spin measured. And this was the very thing that Einstein and others balked at. And although perhaps we should not think in terms of there being communication in the normal sense of the word, I shall continue to use that terminology because it will come into the way some experiments will be discussed later. So just to reiterate, in the scenario as we depicted it at the beginning of this video, two independent electrons, each with definite spin directions in space, come together, and their magnetic moments interact. In so doing, they become entangled such that their spins align in opposite directions to one another. However, the line of that direction cannot be said to be distinct. It is not appropriate to suggest that the pair of spins align in a particular direction in space. Instead, the two entangled electrons have to be imagined to be pointing in any and every direction in space at the same time. This was contingent on the fact that the direction of the spin of one of the electrons had to be always in the opposite direction to the spin of the other. and so we drew them like this, which can't really indicate their opposite spins in any way. They are then considered to be in a single state as far as quantum mechanics is concerned. This is known as the singlet state, a state with zero total spin angular momentum, or magnetic moment, if you prefer to think in those terms. On account of the vagueness of the individual spin directions and from the way the mathematics turns out, this singlet state can be written in lots of ways, which are mathematically identical. Here are just a few of them, using arrows, which pick up on just a few directions in space. This is the version of the singlet state that we usually work with, up, down, minus, down, up, although there's nothing particularly special about that one. The basis vectors that it contained were simply convenient because we preferred to work with the z direction. We could equally well have taken our basis vectors in any other direction. These depictions of the singlet state, and an infinite number like them, pointing in all possible directions, each amount to exactly the same thing, both mathematically and in reality, two entangled electrons. We said that even when these two entangled electrons A and B are then separated, they remain in that entangled state, and it's impossible to think in terms of each electron having its spin in a definite direction in space. All that can be said about them is that the spin of electron A is in the opposite direction to that of electron B. If undisturbed, they remain in that singlet state, like this, or with whatever arrow directions you prefer to draw, and they are still in this state even if the two electrons are separated by incredibly large distances, even if one of them is on the opposite side of the universe. And for this reason, some people prefer to draw them as being connected in some way. These imaginary lines are meant to represent the fact that even though these electrons may be separated by vast different distances, they are, in a sense, one single thing, the singlet state. If, however, someone at A chooses to measure the component of the spin of the A electron in some direction, I'll pick this one, we know there's a 50-50 chance of plus or minus in this direction. And suppose they find, for argument's sake, that the result is -1. This means that the spin of A would definitely be in this direction, upwards in this case, opposite to the measuring device. When that measurement is made, the A points in the measured direction. At that very instant, it would seem, a message, I'll use that word, is sent across the universe, and the spin of electron B points in the opposite direction. How that message travels, what it actually is, whether it is simply just a part of the state vector connection somehow, we have no idea. In fact, when the hidden variable idea was discarded, I think it's true to say that most physicists accepted that the state vector had therefore to collapse in this instantaneous way, giving rise seemingly to this form of instantaneous communication between one electron and the other. The many predictions of quantum mechanics had been so successful that for many physicists it wasn't really necessary to check by experiment whether or not Bell's inequality was violated, or whether or not this seemingly faster than light communication actually took place. However, there were those who wished to try and devise and perform an experiment which would be a kind of Bell test and would specifically disqualify the idea of hidden variables. Perhaps also such an experiment could demonstrate that any communication between the particles must be greater than the speed of light, and in all likelihood instantaneous. And so the next and final two videos in this series will discuss such Bell tests.